All right, great. Thanks for coming to the session. I just want to make sure I flag here. Shuangning Li is really the person I think who deserves the most credit for this work. Those of you who know her know she's incredible, and those who don't should definitely meet her. She's amazing. So she's going to be joining University of Chicago as an assistant professor. Okay, so the talk is, I think, a little different in style, though obviously in experimentation than what you've heard so far. I want you to suspend your disbelief for about like 17 minutes, and in the last minute, I'll try to wrap back to having you suspend less of your disbelief. I think the broad principle is that in many service systems, there's congestion that results from fluctuations in demand and supply, and our goal is to think about how to optimize policies for systems like this at a very, very high level. So I'm going to make that a little bit more concrete. So think about something like a promotional discount in a ride-sharing platform. And the platform is wondering, like, okay, how helpful is that? It's a session on experimentation, so you know that this platform is going to use an experiment. And what they might do is they might send out some coupons, and some people get the coupons, other people don't get the coupons. And what they'll do is then look at the response. But one issue here is that if the people that get the coupons decide that they want to request rides, then wait times get longer, which then has a negative effect on the folks that didn't get the coupons, right? And some of those folks may leave. In general, the wait times will get longer, so people will leave because of that, or people will abandon. And that's something you don't want as an A/B tester, because basically what that means is that the status of the treatment group is affecting the control group. Okay? So in statistics, in experimentation, we refer to that as interference. The treatment that's assigned to one unit might affect the decision made by other units. Okay? So there's been a lot of work, a lot of it at EC, dating back over a decade now, that's looked at this problem in a variety of settings and networks, marketplaces, many other contexts. In our case, what I want to specifically focus on is a particular kind of design that actually Jinglong has written about as well, called a switchback design. The history of switchback designs is hilarious, by the way. It is worth looking back at. It dates back to agricultural experiments where they would try treatments on livestock by alternating, let's say, feed type for the same cow back and forth between two feed types. And the reason is because cows had sort of non-stationarity in how they responded to feed. And so you needed to alternate to make sure that you got a valid estimate of the treatment effect. Today, we use switchbacks for things like ride sharing and delivery platforms. So I'd say the scale has gone up quite a bit from the early agricultural experiments. This is an example of an interval switchback. Just one small comment I want to make technically is that there are different kinds of switchback designs. Some where you deterministically alternate treatment and control. What I'm representing here is something where you randomly alternate treatment and control, and that's why the lengths of treatment and control here are not the same length, because you might have your coin flips come up, heads multiple times in a row. Okay, so the idea here is that if you allocate the entire system to the discount, or the entire system to no discount, then at least while you're running the single treatment for that period of time, you've kind of mitigated the effect of interference, because now everybody's getting the discount for that period of time. There's not really any way for them to interfere with someone who's not getting the discount, except potentially at the switch points. Okay, so clearly there could be some like bias. Oh, that point was not great, but some bias right where the switches happen. Okay. This is widely adopted, like I said, especially by ride-sharing and delivery platforms for testing things like new features, new algorithms, matching, new pricing. So one thing that's pretty common in all the work in using switchback designs is that it's basically structure free. And our goal is to look at whether we can use the structure of congestion to improve the design and analysis of these kinds of experiments. And this is partly why I need you to suspend disbelief, because we use kind of the simplest model of congestion in operations research, which is a single server queue, right? So single server queue, you have basically arrivals happening at a rate lambda Poisson process. There's a constant service rate of mu and some large finite buffer, right? The key thing that we assume is that an arriving customer decides whether they want to join the queue or not based on two things. One of them is how long is the queue, and the other is what's the price, okay? And there's actually a lot of different ways you could model this choice behavior. If we're really focused on congestion, then of course the first thing that comes to mind is that I'm trading off the fact that I have to pay something for the service against having to wait a longer and longer time. But there's other things too that are, fall within this framework, like where, for example, I remember once my wife and I walking by a restaurant with a really long line, so we just got in line. We didn't know what the restaurant was. We're just like, well, there's a lot of people here. It must be really good, right? So that happens too. So you can that both kinds of sort of positive and negative effects can be captured with the choice model. From our purposes, what matters is just that this induces some unknown dependence of the arrival rate on the state of the system and on the price. And this is the thing that the decision maker doesn't know but needs to learn from experimentation. Okay, so in particular, if you think about a queue, then what's happening is if I set the price, that gives rise to this family of state-dependent arrival rates, which gives rise to the steady-state distribution of the queue. Right? What's the metric of interest that this decision maker cares about? Basically, we argue in the paper, and I think it's pretty natural for anyone who works with these kinds of models, that kind of the relevant system metric is the average arrival rate to the system. And part of the reason for that is that you would use that if you cared about revenue, because that'd be price times that average arrival rate. If you thought about social welfare, if you think of a model where sort of consumers' willingness to pay is the thing that's driving their joining decision, it's pretty easy to map that arrival rate to sort of a proxy for social welfare in a setting like this. I won't spend as much time on that, but I just want to say, I think it's pretty plausible that this is a reasonable thing to care about. Now, remember that we're interested in optimizing this metric, and if we're optimizing, we care about its derivatives. So the S demand from the experimental perspective will be the derivative of that B function of the arrival. Okay. All right. So now here's the kind of, I think, first interesting observation, which is how does the fact that you have congestion impact inference? How does it impact running experiments? Okay. So the thing is that two things happen if we take that derivative, and it's just the chain rule. So the first thing that happens is, of course, that every state-dependent arrival rate has some derivative with respect to the price. But the other thing that happens is if you vary the price, you actually change the steady-state distribution of the queue. And that's the first term, okay? In the language of experimentation, we would think of that first thing I described, the effect on the arrival rate, as what's called the direct effect. That's the thing you would sort of directly observe if you ran a naive estimate in the experiment, directly estimate, sorry, if you ran like a naive difference in means estimator from the experiment. But the other thing is an indirect effect, which is this change in the steady state distribution. That's actually very hard to measure, okay, in principle. And switchback experiments are getting around this in part, again, because of this alternation between treatment and control. So let me tell you a little bit about kind of the main things that we do in the paper. So we first kind of do some theoretical analysis that basically focuses on looking on at that single server queuing model, and under some fairly, I'd say, basic assumptions, try to establish some structural insight into how much you can gain from taking advantage of knowledge of how congestion arises. So the main assumptions we make is that the environment is stationary, which is, I'd say, a standard assumption for someone who's a queuing theorist, bizarre for anyone running switchback experiments, because if you're running a switchback experiment, part of the reason you're doing it is that you think there's non-stationarity. So I want to get back to that. That's partly where the lack of suspension of disbelief will come back in towards the end of the talk. Okay, so for now, we'll assume it's stationary, but I'm going to come back to talking about non-stationarity in a bit. The queue length at equilibrium is, question, yeah.
Sorry, just wondering, it's possible that the optimal policy is changing the price over time, right? So is there an issue?
Yeah, so it's absolutely the case that if the world is non-stationary, then changing your price over time may actually be the optimal policy. In the world of a stationary environment, then do you mean, I think, sorry, no, I think you meant something different, sorry, but in a world where the environment is stationary, there is certainly the possibility that I could do much better with state-dependent pricing, where I actually set the price based on the state of the system, right? In here, what we're looking at is sort of a simple one-dimensional pricing policy, where you set the price and then it's state independent. Okay. That's a good point. And partly, I think I want to make, I am going to use like 10 seconds here to just make a more abstract point. I think the way to think about this paper is it's a proof of concept in the absolute simplest setting in which you could make this proof of concept. I'm virtually certain that you could take the kinds of things we're doing in this paper and do them in far more complicated settings. But the real reason to do this is to say that there's something to be gained from taking advantage of structural information in a way that we wouldn't typically do for switchbacks. And I'll return to that if I can at the end. Okay, so to just quickly walk through, there's a couple of other sort of technical desiderata here that aren't nearly as important. And I think one of the things I want to point out is that the type of experiment we analyze is something where you switch between a price wiggle that's a little bit higher and a little bit lower in the treatment and control periods. We consider switchback experiments with intervals are long enough, so we don't have to worry about the carryover bias at the switch points. And I guess the other thing I should say is that we look at an asymptotic regime where the experiment horizon gets large and the wiggle gets small as the horizon gets large. Okay. So this is kind of the first core theorem in the paper, which is that we're able to show 3 equivalent expressions. Now, again, for someone that comes from like a queuing theory background, these are pretty natural, I would say. Maybe not standard, but natural. And they emerge by looking at the same quantity, the derivative of that arrival rate, 3 different ways. One is you could just directly look at it as a model-free quantity. That's basically saying, hey, I have this thing I care about its derivative. Well, that is the derivative, that's the first line. Okay, the second line actually takes advantage of a conservation, that the number of arrivals in the long run has to equal the number of departures in the long run. And there's a very standard identity that relates that to the idle time of the queue called Little's law. It's a special case of Little's law from queuing. And you can use that to obtain the second line there. And the third one is a complicated mess of quantities. But the main way that, the main thing I want to emphasize there is that if you knew that this is an MM1Q, then there's a relationship between the arrival rates and the steady state distribution of the queue. And so what you can do is you can focus only on estimating the direct effects, only estimate the direct changes in the state dependent arrival rates, and then use that to work out what would the changes in the steady state distribution have looked like. Okay, and that's basically what's going on in that third one. And one thing that is interesting there that I'll point out is you get something that looks roughly like the elasticity of the arrival rates showing up in the estimation. The key thing there is I do not need to estimate the change in the steady state distribution to be able to run that third thing. Okay. Of course, I do need to know that I believe that I'm running an MM1Q, which is a very strong assumption. Right. Okay. So let me actually, in the interest of time, I'll skip over these slides. Let's see. Shouldn't be ready yet. Maybe I should just watch that instead of continuing to talk. Okay, so I think I'll skip over these slides in the interest of time, just to say there's a few slides in here that talk through the 3 different kinds of estimation approaches and how we would relate it to the actual data. But I'll skip over that. Basically in this table we summarize that you can translate from the representations that I gave you in that theorem over here to kind of 3 different forms of plugin estimators for each one, using data that just comes from the observations of customers that either got a price wiggle up or a price wiggle down. Okay. All right. So again, just to summarize, basically model-free, idle time based. And what the third one, the one that takes advantage of the structure of an MM1Q, is something I call the weighted direct effect estimate. Again, because of this point that it's only using the direct effects, but we weight in an appropriate way. Okay. All right. So the next kind of important theorem in the paper is something which basically works out a central limit theorem for all 3 estimators. This is the statement of that central limit theorem. Crucially, if you use these sort of interval lengths that are long enough that you don't have to worry about any bias. Jing Long has some work where they kind of think about the carryover bias, others do as well. Yu Chen, who's in the audience, has also done some really nice work on that. In our case, we basically make this assumption on the interval lengths being long enough to get away from worrying about bias. We're really focused on the variance. Okay, so we get a central limit theorem for each type of method. And the next result is something that compares the variances of these 3 methods. And I think this is kind of, there are 2 interesting findings here, okay? One of them is that structural information helps you, which is good. And specifically what we show is that the weighted direct effect always dominates the model-free baseline. But sort of qualitatively, what's interesting here is that it's actually an equality if you're running with a standard MM1Q. And standard MM1Q means the arrival rates don't vary with the states, okay? Which actually kind of what's interesting about that is the more heterogeneity you have in the customer behavior, the better off you're going to be with this weighted direct effect estimator. than with just the black box estimator. And that's that, back to the comment I made at sort of the abstract comment. I think one of the things I want to exhort people to do is in many of these platforms, we have a huge amount of structural information, okay? And we just throw that all aside. We run black box estimators when we're running switchbacks. And even I think like some step forward in taking advantage of that structural information is almost certain to be beneficial for at minimum for variance. The other really interesting finding, this is I think it tickles the theorist in me, but it's a really nice finding, is that the idle time estimator and the weighted direct effect estimator have an incredibly elegant relationship to each other where one has half the variance of the other. The weighted direct effect estimator is half the variance of the idle time estimator. And that's really interesting because the idle time estimator is not using a ton of structural information. It's only using this conservation law that's sort of standard to a queuing system. And that actually is something you could use even if the system wasn't Markovian. So you have a lot more robustness built into it, right? So this is kind of, I think the other thing I would say here is it's saying even a little bit of taking advantage of structural information, this is a queuing system, is already helping me a lot. It's getting me within a factor 2 of this weighted direct effect estimator, okay? All right, so here's an example where the joining probability of a customer follows a power law, okay? Where basically with respect to the state, that's the equilibrium distribution on the left, and you can see that both the weighted direct effect estimator and the idle time estimator have a huge advantage over the model-free estimator. All right, now this is the MM1Q, but skip over that. Okay, so I think I'm doing all right. Do I still have a few minutes?
4 minutes.
Oh, wow, fantastic. I'm going to slow down. So, okay, I'm doing good. So I wanted to get to non-stationary because I think this is like one of the things that's important to know about our EC paper is it was submitted without non-stationarity in it. And if I'm being honest, I was surprised at some level because if I wrote a paper on switchbacks without any mention of non-stationarity, that would probably have been the first question I had. When people run switchback designs in practice, as I said earlier, really non-stationarity is a fundamental concern. It's the main reason that they have intervals that are anything more than 2. Because if the world is stationary, then the best thing you could do is just divide half your time into treatment and half your time into control. So right, like on that slide where I told you we use intervals of length greater than t to the 1/2, that's a little weird. Why didn't I just tell you I use half the time for 1/2 time for the other because the world's stationary? The real reason in practice people don't do that is because the world is non-stationary. Okay, so what I want to do is talk a little bit about what we've been doing since we submitted the EC paper, and this is really where the status of things is now. And this is a very exciting development, I think, to start thinking about what happens in a non-stationary environment. So here I'm going to be presenting just some numerical results that are some simulation results that come from data calibrated based on emergency room arrival rates. This is from a very nice data set at the Technion, the Service Enterprise Engineering Center, where they maintain a number of different service system data sets. And this is one half-hourly arrival rates to an ED by day. Okay? And clearly very non-stationary. All right, so the first thing we should see here is if we vary the arrival length, then the estimation error is non-monotone in the interval. Okay, and this is for the model-free and the idle time-based estimate. Already interesting because clearly there's dependence on the interval length, right? Now, part of what's going on here is it's actually a little subtle and nuanced how the interval length is affecting them. So when you have a larger switching interval, okay, then what you're benefiting from is this like getting rid of the bias at the switch point that I mentioned. That's a lower carryover effect from mixing of the Markov chain. But you have a larger bias due to non-stationarity. Exactly what I said. Why would you not just split the time in half? That would be stupid if it looked like the thing I showed you previously. Right? Now, on the other hand, if you use very small switching intervals, then you're benefiting from not having that non-stationarity. It's like I'm totally calibrated to exactly the state of the world right now, but massive carryover effect. This is why you can't just run naive A/B tests and get away with it. Lots of interference. So the thing is that the weighted direct effect, remember, is taking advantage of only estimating direct effects. So the question is, does that get me a little bit out of this hole? Am I immune to rapid switching? All right. So what we do is we construct a weighted direct effect estimator in a non-stationary setting by introducing one additional parameter called a kernel length. And it's not as sophisticated as a kernel, like for those of you that are machine learning experts. Literally all we do is take the time horizon and divide it into windows. The length of that window is the kernel. Okay, so now I'm running an interval switchback. And on top of that, post hoc, I compute a weighted direct effect estimator by basically averaging and computing this WD estimator within windows of kernel length. And these are different kernel lengths. Putting aside the kernel length, the main thing I want you to see is it is monotone in the interval length, which means I can run switchbacks with short intervals, right? So kind of a key takeaway for us was, well, why don't you just send the interval length down as small as you can? And what do you get if you drive the interval length to 0? What you get is a customer level experiment. You just switch on the customer level, right? When you combine that idea, so now you're effectively running a naive design, right? You're just randomizing at the customer level. But you combine it with this windowed weighted direct effect estimator, you get exceptionally good performance, okay? And kind of what we're showing on the right-hand side here is the performance. The plots are a little tricky because the left one, the x-axis is interval length. There's no kernel length for the model for your idle time estimator. On the right, it's the weighted direct effect estimator with this 0 interval length. And the x-axis is the kernel length, okay, that we vary. And what you see there is that you get, the best performance if you use WDE with an optimized kernel length. One thing I want to point out that's really cool about this is you don't need to know in advance what the optimal kernel length was. You can actually do some post optimization to find the kernel length that you think looks best given the non-stationarity of your data, right? So, I'll leave the summary slide up, but I think what I want to return to just the last minute or something is that, when I first was kind of involved in this project, the appealing thing to me was exactly this point that I made, that I think there's a lot of value for structural information. But I guess where I'm at now is I realized I had a conversation with someone that works at an autonomous ride-sharing company recently. And if you look at that service, they know everything. There's only one thing they don't know, and that's demand elasticity. So yeah, I'm using an MM1Q, but I think with the right engineering team, you can actually build a high fidelity simulator that basically lets you implement a WDE estimator for an autonomous ride-sharing service that can take advantage of the structure, right? And I say that only to point out to people that yes, like it's super stylized, super simplified, and there's this simplicity in the policy and so on. But I think the main point that this is getting across is if we would not have gotten to a new estimator in the non-stationary setting without looking at the absolute simplest thing in the stationary setting first, right? So I think for me, what's very exciting here is like we have this like new toolbox now for how you can approach switchbacks in a non-stationary setting that has potential, I think, for much higher power experiments. And switchbacks historically have been highly underpowered, so there's a lot of opportunity here. So I'll stop there. Thank you. And I think I'm the only one standing between you guys and the industry.
So what you showed in the end, is it you literally randomize person by person, or you still do the switchback design?
No, yeah, that's a great question, actually. So the SB0 literally would just be randomizing person by person.
Okay.
And the only reason I called it SB0 is to embed it within the family of what the rest of the design
And
was.
it has as good performance as a, let's call it the well-estimated switchback design with non-stationarity. This is kind of what.
So that's kind of what that last slide is
Yeah.
showing, right? Now you want to be a little bit careful because one thing I didn't open the hood on
Right.
is what do we do with these calibrated arrival points, right? So we're feeding them into a queuing model in which there needs to also be a choice process on the part of customers.
I'm asking because you started kind of, I'm trying to make switchback designs better, but then you said, then we're going to completely throw them out.
Yeah,
I mean, works, right?
Yeah, I think it's like the interesting thing to me is that, where that lands anyway is you get to this completely like high frequency thing.
Right.
One thing I will say is that, for a lot of other types of interventions that might not be tenable. So here we're interviewing on price, right? But if you think about something like a matching policy, you may not be able to just do a customer by customer switch back. So what do you do there? I mean, even there, I would argue you could probably drive the interval length down much shorter, not worry as much about the carryover effect bias, and take advantage of structural techniques to build an estimator. So that's part of the reason I think to call it an SB something, just because I think that's the higher level takeaway, especially when one starts thinking about more complex policies than just a single dimensional pricing change. So, yeah. That's a good question though, good catch. All right, oh, sorry, yeah.
Yeah, I have a question regarding, so basically, right now, the whole model just use the kind of like the M1 cube structure, and I think that's the only thing that's being assumed here. And the question, so what if I have more covariant information, such as like the environment? So maybe like I have multiple, like, instead of just like, let's say one.
Yeah.
Let's say multiple places, I definitely know they have different characteristics for the cube. And how can I incorporate those kind of?
Yeah, this is a really good question, which I think is less about queuing and more just generally about what it means to have a non-stationary model. So let me at least let me get out of the model of this talk and actually talk about Yuchen's work or like model where there's a much more general sort of just underlying Markov chain. And I think then the question just becomes how much of the state of the Markov chain that's driving the world do you actually know? Because whatever you don't know is non-stationary, right? And I think there's not really a great answer to that except on a sort of applied case by case basis. If you're in a world where you think you observe enough state information to account for the non-stationarity, then you're not in a non-stationary world, you're in a stationary. And in that case, actually, you should do the things you would do in a stationary world. So if you were committed to running a switchback, you should only switch once. But there's actually better things you can do if you really believe the world is Markovian with respect to what you observed, right? There's a lot of other estimation techniques as well. On the other hand, if you're in a world where what you observe accounts for a very small fraction of non-stationary, where there's lots of idiosyncratic variation on a day-to-day basis, then fundamentally, I think you're in a place where you need to worry about the kind of bias variance trade-offs that people historically have thought about for switchback designs. And that would be the kind of thing that leads you down the road of asking, sort of like, I guess I would say in that case, the additional covariates aren't really fundamentally going to change your approach. Does that make sense?
Yeah.
So I think you kind of land in one of these two extremes. It's either you're in a world where you think you're fairly stationary or you're not. And I don't know that I don't know that much beyond that is worthwhile. Yeah.
So your last result relies on this queuing model really accurately captures the interference behavior.
Yeah.
What do you think about like model misspecification potential impact?
Yeah, I mean, I think that's a really good question. So I think those are actually two separate questions. I just want to be clear, by the way. I mean, there's one question about interference through aggregates. That's key. I do think that that's sort of fundamental to what this kind of approach is benefiting from. Like you're using a structural approach. I think it's important that even if one looks at, for example, social network models of interference, if you were going to benefit from a structural understanding of the social network, it would have to be at some level of aggregation, where that kind of aggregate understanding of network interference behavior is what's allowing you to debias. So I think that's an important point, and I would almost say, yeah, like that's a sort of a constraint on the kinds of things that we're dealing with here. So that's the aggregation point. The second one about model misspecification, I think at some level, I feel like the whole talk is really about that. It's saying, if I can take advantage of structure I believe and that structure is correct, I can actually make a lot of headway. But the main result in the paper and the talk that hits at model misspecification is that idle time-based estimator result. Because virtually any system that exhibits queuing behavior and is work conserving is going to obey some version of these conservation laws, in which case you're getting within a factor 2 of what you would get if you could completely unpack the invariant distribution. So I think that's sort of an interesting way to think about model specification. One thing that, because our work on non-stationarity is relatively recent, one thing that we haven't sort of said as much about is what happens to an idle time-based estimator if you move into this non-stationary regime. And you have to be a little bit careful there because there's a question of what timescale is the system stationary enough over that the idle time-based estimator is sensible. It'll be related to Ron's question about exactly what the timescale switch is.